Hello everyone, welcome to the course on large language models. So in today's lecture we are going to talk about neural networks basics. So as usual this is not possible to cover neural network deep learning in a single lecture. So the aim of this part is essentially to give you a very brief overview of neural networks, how these networks operate and what are the ingredients of these networks, right? Because at the end of the day large language models are also neural networks, deep learning methods. So I thought I should also give you some ideas about neural networks, although there are many open source lectures available on YouTube. There are many good lectures available on NPTEL also on deep learning neural networks. You can refer to those lectures, but here I'll just give you a very brief of the neural network in general. Okay, so when we talk about neural network, it basically goes back to long time back during World War I, World War II, 1940s, 1943s. Those were the time where people started thinking of how to mimic human brain using computational approaches, right? So if you look at the history of neural networks, it goes back to 1943, 1944, during that time when McCulloch and Pitts. So McCulloch was a neuroscientist and Pitts was a logician. Now interesting fact to note here is there is no computer scientist involved. Remember, the time is 1943, before Alan Turing's invention. So at that time they thought of designing a very simple approach to mimic the way neurons essentially interact. Okay, and they came up with a simple method, a simple model called MPNet. McCulloch's M and Pitts P, MP network, MPNet. I'll discuss MPNet later. And then in 1957, 1958, the years may not be correct, by the way. So this is just 1957, 1958. During that time, Frank Roosevelt, right? So he proposed the idea of the perceptron. Okay, Frank Roosevelt. So he proposed the idea of the perceptron, which is considered to be the first neural network, a realistic neural network proposed. Some people often call Frank Roosevelt as the father of neural network, but there are debates. And then later on, around I think 1965, 1966 or 68, during that time, multi-layer perceptron was proposed. So this is a single perceptron, now multi-layer perceptron. We'll discuss all these models in today's lecture. Multi-layer perceptron, one proposed. So this was proposed, and Frank Roosevelt, so he said that, so he speculated that the perceptron may eventually be able to learn, to make decision, and to translate language. Okay, this was kind of a speculation at that time. 1968, MLP was proposed. It's called MLP, multi-layer perceptron, right? And later on in 1960, I think 1969, Minsky and Papert. So Minsky, some of you know, Minsky is also called the father of computer science. He was the founder of AI lab at MIT. Minsky and Papert, they identified a serious limitation of perceptron. They showed that a very simple function called the XOR function, right? A XOR function, cannot be modeled using a simple perceptron, right? And that was a huge setback, because right after that, kind of AI's research got stalled for almost 20 years. Okay, and this time is called the AI winter time. I think 1969 to 1986, right, during that time. Then after 1986, I think around 1986, the famous backpropagation method was introduced. All of us know that backpropagation is essentially the building block of all the training protocols that we use in today's neural network. And 1989, I guess, 1989, 1990, during that time, it was shown that this multi-layer perceptron, right, is capable of approximating any kind of non-linear boundaries that you can think of. And that in that year they came up with an idea of universal approximation theorem. Universal approximation theorem, UAT, was proposed, and it was said that a multi-layer perceptron with a single hidden layer can be used to approximate any continuous function, right, to any desired precision, right. So a multi-layer perceptron with a single hidden state, a single hidden layer, can approximate any continuous function. And this was a big claim, by the way. This was a big claim because now we can use MLP for any non-linear classification that you can think of. By the way, I'm not going to details of this theorem. As I mentioned, this is basically introductory part. So if you are interested in understanding all the details of this, you should basically go through a formal deep learning course. Nevertheless, this is a very brief introduction of the history of neural network. So when we talk about neural network, right, the term neural network is there. Therefore, it has some connection with neuron, right? So that time, 1960s, 1970s, 1980s, 1990s, even 2000, early 2000, there had been a huge effort to essentially mimic the way human thinks, right? How neurons interact. Now, it goes back to, I think, 1860s or 1870s, where when people understood that human brain essentially works through interactions of neurons, right? And neurons collect signals from the environment, from other neurons, and these neurons essentially pass signals, do some computation. Of course, computation is a very vague term, but neurons basically do some operation, and that operation is fed to the other neuron as a signal, right? So I think all of you are aware of biology, the basic neuron structure, right? There are this, you can think of these neurons which look like this. I'm very bad in terms of drawing things, but you can think of these neurons, right? Right. So this is one neuron, and this is called axon, right? And you have this dendrite, and this is called synapses, right? So where two neurons through which two neurons essentially interact. You can think of another neuron here, right? Sorry for the bad drawing, but yeah. And through synapses, you collect signals from other neurons, you pass it through axon, and then you basically do some processing here. This is the central part of neuron, which is called soma, right? So essentially the dendrite, they receives signals from other neurons, right? Synapses, they so these are the point of connection to other neurons, point of interaction. Soma is essentially responsible for processing the information, and axon is responsible for transmitting. So it transmits the output of a neuron, right, to another neuron. Now in this way, if you think of it in a very, very high level, right, you have some neurons which are essentially collecting information, right. You have some centralized system, which is the soma in our case, which processes this information, and it passes this basically it does some processing, it outputs something, that output moves to the next neuron, right. So you have some inputs x1 x2 dot 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 xn. So in here you do some processing, right. You can think of the processing as a function, right, which is parameterized, which is basically which takes x1 x2 xn as inputs and produces y as an output, right. So this is a very simple, simple way of describing this complex neuron structure. So now the MPNet, right, which was proposed that time, as I mentioned earlier, this McCulloch-Pitts method. So the MPNet was essentially designed to mimic this simple system. Okay, so for an MPNet, what you have now, this is MPNet, McCulloch-Pitts network. You have inputs. Now these inputs are binary. Okay, these are basically either 0 or 1. Okay, this is MPNet, the simple neuron structure that you can think of, right. And then what it does, it essentially processes this here, right. I'll tell you what they mean by processing things, and it outputs something called y. This is also a binary variable. Okay, so what it essentially does, it basically takes the sum of all these inputs, sum of all xi's 1 to n number of inputs, in this case 3 inputs, right. So and let's say you have a function here which is, let's say, g, right. You pass it through g, right. So if, let's say, if the sum is greater than equals to certain threshold, right, you produce 1, otherwise 0. Okay, a very simple structure. And with this, now this is a linear, as you see, it's a linear function, right. Now with this you can it's basically a step function, right. So with this you can think of modeling different types of operations, right, boolean operations, boolean functions. For example, let's say AND. Okay, we know that AND, this AND operation, x1 x2 is input, y output, 0 0 0 0 1 0 1 0 0 1 1 1. Okay, so how do we use MPNet to essentially mimic AND operation? So if you want to mimic AND operation, what is going to be theta? Think about it. Your input here, there are two inputs, right, x1 x2, right, and this is output y. Okay, what is going to be my theta? So if both these inputs are 0, it will produce 0. If one of them is 0, it will produce 0, right. If both of them are 1, it will produce 1, right. So the threshold can be 2, right, because 0 plus 0 is 0, this is less than 2, it will produce 0. 1 plus 0 is 1, less than 2, it will produce 0. 0 plus 1 is 1, less than 2, it will produce 0. And 1 plus 1 is 2, this is this is equals to 2, it will produce 1. Okay, so to mimic AND operation, the function that is going to be learned is essentially very simple. x1 plus x2 should be greater than equals to 2, right? So the line is x1 plus x2 equals to 2, and anything above this would be classified as 1, otherwise 0. Okay, now if you think of the vector space, right, you have 4 points essentially, is x1, x2. So let's say this is 1 1, right? This is 1 0, this is 0 0, this is 0 1, right? So this should be, for here y equals to 1, y equals to 0, y equals to 0, y equals to 0. Okay, and the line that you have drawn would look like this. It will essentially touch this point, x1 plus x2 equals to 2. Now in this same logic, if you want to mimic, let's say OR, which is 0 0 0 0 1 1 1 0 1 1 1 1, what is going to be the theta? The theta, think about it. Okay, it's very simple. The theta is going to be 1, right? If any of them is 1, it basically attains the threshold theta, then it will produce the output 1. So in that case, the line would look like, so for this one, now this is 1, y equals to 1, this point, this is y equals to 1, this point y equals to 1, this point y equal to 0, and the line is x1 plus x2 equals to 1. Okay, so it will basically would look like this. So MPNet is great when you have kind of boolean inputs and boolean output, right? And data points are linearly separable. Okay, now why I said that data point is linearly separable, think about it here. So in both AND and OR, we have seen that a linear boundary can separate data points, right? But think of a complicated function, a relatively complicated function, let's say XOR. Okay, 0 0 0 0 1 1 1 0 1 1 1 0. Okay, if you look at this diagram, here y equals to 0, y equals to 1, y equals to 1, y equals to 0. So this case, there are 4 data points. You will not be able to classify these 4 data points with a linear boundary, with a line, right? And this was the setback. This was observed by Minsky and Pippert that time, 1968, 1969, and they said that perceptron is useless because this is not able to classify a simple XOR or mimic a simple XOR operation. Okay, later on, this MPNet is not very suitable, right? Therefore, the perceptron was proposed in 1957, right? Perceptron is also not able to mimic XOR, right? What is perceptron? How it is different from MPNet? Let's look at it here now. So the perceptron, not very different from MPNet. Inputs here, let's say x1, x2, x3. Inputs are real numbers. They may not be Boolean. Okay, and now with every input there's a weight, w1, w2, w3. Okay, what does this weight indicate? The weight indicates the preference, right? Let's say the decision is whether you want to go to watch a movie or not, right? This is a decision that you need to take. And what are the inputs? The inputs are, let's say, the hero, right? The director, the duration of the movie, and so on and so forth. These are the inputs. These are the features, right? Now, in case of MPNet, we have seen that all these inputs are equally likely, right? They are basically summed up, right? That means their importance are equal. Now in this decision process, oftentimes what we have seen that some features are more important. For example, let's say for me, I'm a Shah Rukh Khan fan, right? And let's say if I see that there's a movie where Shah Rukh Khan is a lead actor, I will definitely go irrespective of the duration, right? The director and so on and so forth. So for me, the most important feature is who is the hero, right? Because I am a die-hard fan. Whereas let's say there are other people who actually look at the other aspects, the director, right? Let's say the producer, I don't know, maybe the also the cost of the ticket and so on and so forth. For them, the other features are important. So therefore, considering all these features equally may not be a good approach. We should also introduce weights, and weights were introduced in perceptron. Therefore, now your sum here, in the central part of the neuron, right? I will still call it a neuron. Remember this, today's deep network, for example, all these LLMs, they are, I mean, if you call them neural network, then people will essentially kill you, okay? So they are just non-linear functions, right? Generative AI, all non-linear functions, that's all. So there was a time, 1960s, 1970s, during that time when people essentially tried a lot to mimic human brain, but these days nobody cares about human brain, right? The task is essentially to make this models more complex, more effective, and so on and so on. It doesn't matter whether they mimic human brain or not. So here the sum is like this: W1 x1 plus W2 x2 plus W3 x3, right? Along with this, there's a bias term W0. We have seen, all of you know, right? In machine learning, we always use this bias term for many purposes, right? So we have this bias term W0. Okay, so now this sum will essentially be fed to some function g, right? We have seen this z function or g or f, whatever, right? I think we use g here. So this function will be fed to a g, and the output of g will be given to y, right? Now in case of perceptron, g was essentially a function which would look like this. So g of x is -1 if x less than 0, it is 0 if x equals to 0, it is +1 if x is greater than 0, right? So this function is called signum function. This is called signum function, right? So you take this input and process it, right? And if the input value is greater than 0, it will produce 1 as an output, right? Otherwise, -1 or 0. So later on, when we again reformed this perceptron, we observed that we don't need -1, 0, +1. There are two levels which are enough. So we modified this. We said, okay, let us use this modified function, which would look like this, which will produce 1 or which will produce 0 if x is less than 0, otherwise 1 if x is greater than equals to 0, right? So we are happy with two levels, 1 or 0, because remember these methods are proposed for classification, mostly for binary classification. Okay, so this is perceptron. You have inputs, weights. You add those you basically sum them up, multiplied by weights and sum them up, and pass it through a signum function, and it will produce the output. Okay, so if you do that, let's see what happens with AND, right? This AND. So right, so what are the parameters that we need to learn here? The parameters that we need to learn here in this case, all these W's and W0, weights and bias. Okay, so to learn to mimic AND, right? There are two inputs, x0 and x1, whatever, x1 and x2, right? So this is W1 x1 plus W2 x2, right, plus W0, right? You pass it through the signum G. And how do we in case of AND, let's say if W1 is 1, W2 is also 1, right? W0 is minus 1.5. Okay, so it will essentially be, think about it. So this will look like x1 plus x2 minus 1.5. So this is my classifier, right? The line. If x1 and x2 are 0, both of them are 0, then this is going to be minus 1.5, which will be this, which will satisfy this, so the output will be 0. If one of them is 1, then this will be minus 0.5, right? This will again be 0. If both of them are 1, then this will be plus 0.5 and this will be 1. Okay, so it is able to mimic AND, right? Similarly, you will see to mimic OR, W1 should be 1, W2 should be 1, and this bias term W0 will be 0.5, and you will see that it will essentially, with this parameters, will be able to mimic OR. So whatever functions that MPNet can mimic, perceptron can also mimic, right? Here the advantage is that we have weights. You can give advantages to more emphasis to certain weights, certain functions, certain inputs, and less emphasis to certain features. But the problem remains the same. This XOR, right? It is not able to classify XOR because, remember, there is no nonlinearity here. These are all lines, right? The 2D plane line, if you see 3D plane, a plane, right? 3D coordinates, a plane. There is no nonlinearity. This G, right, is still a step function. So how to address this XOR function, right? So then, McCulloch and other scientists, they came up with the concept of activation function, right? I intentionally have not used the term activation so far, right? Although, all these G's, right, all these G's used in perceptron, MPNet, they are all activation functions, but I have not used them so far intentionally, because when we talk about activation, we mostly refer to a non-linear activation. Okay, the activation function, or it's also called transfer function, right? So and this activation transfer function is mostly used in multi-layer perceptron. So far we have talked about basic perceptron. Now we are talking about multi-layer perceptron, MLP. MLP is used in transformer, by the way, everywhere. In MLP, what is the specialty here? Now here you have a concept of layers. Okay, input layer, hidden layers, right, and output layer. Okay, x1, x2, x3, for example, there are 3 inputs, right? All of them are connected. So this is also called feed forward network. All of them are connected to each other, right? All of them are connected to each other. It's a mess, right? So yeah, okay. Now, so this is input layer. This is the first hidden layer. This is second hidden layer. Okay, and this is output layer. Now, if you notice my drawing, I have intentionally made 2 different hidden layers with different number of neurons. In the first layer, there are 5 neurons, 1 2 3 4 5. Second layer there are 4 neurons. Okay, now each of these neurons itself is a perceptron, isn't it? If you look at this one, inputs are coming here, right, and it will generate some output. Now this output is fed to all the other neurons in the next layer. Okay, and with every connection there are weights. These are weights, right? And here notations are very important, by the way, so you can use any convention, but here in this lecture we will use a specific convention. Let's say input 1 is connected to input neuron 2, right? So the weight will be W21, right? So if xi is connected to a neuron whose index is j, the weight is going to be wji. This is the convention that I follow, right? And there are different layers. Since input is in this layer and hidden state is in this layer, so the weight will be for layer 1. So the superscript indicates the layer, right? For example, let's say this specific weight, right? Now this is connecting ith neuron in this layer, right, first layer, to jth neuron in second layer. The weight is going to be wji 2, right? So this one will be wji 2 and this one is wji 1. Okay, so we assume that there are n number of, again notations are very important, so pay attention to the notation. There are n number of inputs, x1 x2 ... xn. There are k number of outputs, y1 y2 ... yk, capital K, and there are, let's say, m number of neurons, in a hidden state. And let us assume, just to make things simple, let us assume that there are layers and every layer there are equal number of neurons, let's say m number of neurons. Okay, so the number of layers in a neural network is called the depth of the neural network, and number of neurons in every layer is called the width of the neural network, and these are hyperparameters that you need to fix to start with. Okay, now we see that how this MLP can mimic the XOR operation. Okay, two inputs, x2, right? Let's say there are two neurons in a hidden state, right? Okay, and one output y. Okay, so now how to calculate the weights and biases, right? We'll discuss later when we talk about backpropagation, but let us assume that the weights are as follows. This is 1, this is also 1, this is also 1, this is also 1. Okay, and biases here is minus 1.5, this is also minus 0.5, and this is 1 weight, this is 1 weight, and with this neural network, this is with this perceptron, the bias is minus 0.5. Okay, now this is the structure, right? Now this structure is enough to mimic the XOR operation. Okay, let me redraw again. So x1, x2, h1, h2, y is 1, this is also 1, this is 1, this is 1, right? The bias here minus 1.5, there's a bias here minus 0.5, 1, there's a bias minus 0.5. So think about it, x1, x2, right? And here also we use the modified signum function as an activation. 0, 1. Okay, what is h1 here? So h1 is the signum function, modified signum function, 0 times 1 plus 0 times 1, the weights, these are weights, this one and this one, right, minus 0.5. okay, and the output, so this is minus 0.5, so the output will be 0. Similarly here you will see the output will be 1, this is 1, this is 1, this is the output of h1. So h1 essentially acts as a OR. h2 is what? h2 is signum, right? 0 plus, okay, you will see this will produce 0, 0, 0, 1. This will act as an AND. Okay, output here y is again signum, is gn. There's a small mistake here, this should be minus 1. okay, the weight here is 1, this weight is minus 1. Don't worry about how we came up with this weight. Let us assume that the weights are known to us. Later on we'll see how we came up with this weight. Okay, so this is essentially h1 minus h2 minus 0.5, right? This is minus 1. okay, and if you do the calculation you will see that this will produce 0, this is 1, this is 1, and so this is 0, this is 1, this is 1, and this is 0. okay, so now with multilayer perceptron we will be able to mimic this XOR, which is the beast, right? The XOR function. So far we have discussed basic architecture of perceptron, multilayer perceptron. Now let's focus on activation functions, which is activation function is essentially the core part of neural network. Okay, so but before that let us look at the architecture once again. Multilayer perceptron, let's say there are two layers, two hidden layers. So sometimes we don't consider the input layer and the output layer as hidden as layers. So when you say 3 layers, we basically refer to 3 hidden layers. Okay, so yeah, right, these are inputs, right? I'm not drawing all the connections, right? We know all the connections are there. Let's say there are n number of inputs, as I mentioned, x1, x2 dot 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 xn, right? There are m number of neurons, okay, also connected, and there are k number of output. Okay, and the notation, the convention that we followed is that, let's say there's a connection from ith input to jth neuron, the weight, corresponding weight will be W of ji, layer 1. Okay, so at every neuron there are essentially two operations that are happening, that are going on. One is this aggregation operation, right? It aggregates all these inputs, right? Aggregation is just a sum, a weighted sum, and then we have an activation function, right? So aggregation operation is denoted by A. Okay, so let's say at this neuron, at the jth neuron of the first layer, so AJ1, so AJ is the aggregation, right, for that neuron. So this is sum over all the inputs, I equals to 1 to n, right? Wji 1 xi. Pay attention to the notation again, right? And we have a bias J0. Now this bias is fixed for a certain neuron. For this neuron, for jth neuron, the bias is Wj0. Let's say for ith neuron, the bias is Wi0, and so on and so forth. So this is the aggregation. So after the aggregation, what happens? After the aggregation, it will essentially be passed through an activation function, right? So the activation function is denoted by, let's say, H, right? So HAJ1 is the output of the activation function, and let us denote it by Z of J1, right? So Z is the output of the activation function of the jth neuron, right? So A is called pre-activation output and Z is called post-activation output, or whatever, activation output. Okay, so now this activation function is very important. So far in case of perceptron, impinate, this was just a linear function, step function, right? We'll discuss about this activation functions in today's lecture. But before that, so here all these Z's will be computed here in layer 1, first layer, and the second layer, what will happen? Let's say in second layer there is a neuron which is, let's say, the jth neuron of the second layer. For this neuron, what is going to be AJ2? This will be sum over, right, all M, because there are M neurons which will basically produce outputs, and all those outputs will be fed to the next layer, right, to every neuron of the next layer. So M ranges from 1 to M, right? JM to ZM1. Okay, plus the bias J02. Please pay attention to the notation. Okay, this is very, very important. Try to memorize the notation if possible. So this is the pre-activation output for the jth neuron of the second layer, right? Let's say this is the guy, right? Jth neuron. Okay, the Z, the post activation, the activation output will be H, right? Now what is going to be, so this is the second layer. Now the output layer, let's say YK, yk is what? Yk is going to be sum over, again let's say there are m number of neurons in the second layer, m equals to 1 to m, right? W km zm2 plus w k02, right? So this is the output. Okay, so if you understood the notation, let's now move on to this activation function h, right? So the basic activation function that you can think of is the step function that we discussed, right? So let's say a linear activation function, a linear activation function. Let's say gx equals to x. Okay, if we take the derivative of this activation function, why do we need to take the derivative of the activation function? Later on, when we'll talk about backpropagation, you will see that these derivatives would essentially contribute to the weight update. Okay, we need to take the derivative of the error function with respect to different weights. Now when we take the derivative of the error function with respect to the first weight, for example, you need to follow the chain rule, right? So whatever actually follows between the weight and the error, all those components will be considered while taking the derivative, right? And one of these components is going to be this activation. The derivative of this activation is very important, right? Let's say you have an activation like gx equals to 1, okay, a constant activation function. Whatever you input you give, it always produces a number, a constant number. So the problem here is if we take the derivative, right, this will be 0. Okay, so 0 derivative doesn't make any sense. If we have a linear activation like this, gx equals to x, so if you take the derivative of this, g of x equals to g dash of x is going to be 1. This is again a constant derivative, so constant contribution will be added or subtracted, right, to the existing weight. That is also bad, right? So therefore what people thought is that this is the right place to introduce non-linearity. So what are these non-linear activation functions? The simple non-linear activation function is the sigmoid function, which you all know. The sigmoid, this is used heavily, right? 1 by 1 plus e to the power minus x. Okay, so and we know that the sigmoid essentially right, essentially squashes everything between 0 to 1. This is 0.5, this is 1, this is 0. So whatever input you give is x, and this is sigmoid x, y axis is sigmoid x. Whatever input you give, it always squashes everything between 0 to 1. The good part about sigmoid is that you take the derivative of this, let's say g dash x is sigmoid into 1 minus sigmoid. You don't need to compute the derivative explicitly. If you know the sigmoid, you will get the derivative of the sigmoid very easily. So this is a good activation function. The problem here is as follows. The problem here is the derivative, if you take the derivative of sigmoid, if we draw it, right, you see it would look like this. Okay, at 0 you see that the value is 0.5, and then after certain threshold, so this is x and this is g dash x, the derivative of the sigmoid. After certain threshold, you see the value of the derivative is very, very small, right? This is generally minus 3 and 3. If the input is less than 3 or greater than 3, you see that the output will be very, very small. That means it will contribute to the weight update, very, very small. And this would further lead to vanishing gradient and all the other problems, right? Vanishing gradient problem, we'll discuss in the RNN part of it, right? So this is the first problem, vanishing gradient problem. This is not exactly the vanishing gradient problem, but let us refer to it as a vanishing gradient problem. The gradient will vanish slowly. The second problem is that the sigmoid is not symmetric around 0, right? This is not symmetric around 0. What do you mean by symmetric around 0? Let's say instead of this function, if we had a function like this, okay, something like this is 0. So this is symmetric around 0. Why this is important? This is important because we'll see later that generally symmetricity is always important, always good. Okay, so this is not symmetric around 0. How to address this? To address this, people came up with another activation which is called the tan H activation. This is a hyperbolic function, right? So tan H is g of x e to the power minus x, okay, and the derivative of this g of x is essentially 1 minus tan square h, tan h square x. Here also you don't need to explicitly compute the gradient. So tan h, what it does, it squashes everything. So tan h, so this is the tan h function, right? It squashes everything between -1 to 1, unlike sigmoid, which reduces everything to 0 to 1, this essentially reduces everything between -1 to 1. And this is symmetric. The bad news here is, here also you see the same kind of plot for the derivative. Okay, this is 1. After certain threshold, the value tends to be very small. Okay, tends to become very small. So the same vanishing gradient problem may occur. Meanwhile, people also started using, so this is 1, this is 2. The third activation is softmax. So we all know what is softmax, right? Softmax is used everywhere. So softmax is essentially g of x, basically x1, x2, dot xn e to the power x1 by sum e to the power xi. Okay, it produces a probability. The other popular activation function is ReLU, rectified linear unit, and it is used everywhere. It is very popular. What is ReLU? So ReLU function is very simple. Fx equals to x if x is greater than or equal to 0, otherwise 0. That means it chops off all the negative values, right? It looks like this. Positive values are linear, so this is x, this is fx, and otherwise 0. Okay, so now this is very interesting because this is a very simple activation function that turned out to be very effective. But here the problem is as follows. So let's say if the weight if the input is negative, right? Now remember, this activation function is applied on top of A. What is A? A is the pre-activation value. So if the pre-activation value is negative, there will be no activation. If it is negative, it will be 0. Post-activation, this will be 0. It means that that particular neuron will be dead, right? So this is called dead neuron problem, and that's bad, because you expect that the model should be able to capture the negative part, the positive part suitably, right? So if we take the derivative of this will produce 1, and this is again 0. So constant addition for positive values, but zero addition for negative values. This dead neuron is a bad news, about ReLU. To address this, many variations of ReLUs have been proposed, right? Leaky ReLU. Leaky ReLU is one variation which essentially says that f of x is x, otherwise 0.01 of x, right? You give some weightage here, so it basically looks like this, and some weightage to the negative part also. So this addresses the problem of dead neuron, because you have some value for this negative pre-activation neuron. There is something called parametric ReLU, where instead of fixing this to 0.01, we make this, where a is a learnable parameter. Now sometimes you can see, or you can say that negative part is bad, but we should also capture negative part in some ways. So instead of taking ReLU of x, can we take the ReLU of minus x, right? That would solve the problem of the negative part, right? So another variation of ReLU is proposed, which is called concatenated ReLU. Now here it will produce a vector of size 2. Okay, the first vector is ReLU x, and the second component, the first component of the vector is ReLU x, the second component is ReLU minus x, right? So ReLU minus x will essentially capture, if the pre-activation value is negative, it will be positive, right? There is another variation called ELU, exponential linear unit, right? It is x, f of x is x if x is greater than or equal to 0, otherwise alpha e to the power x minus 1. They introduced this exponential component here. So now these are small variations of ReLU. Let's look at some of the major variations of ReLU, right? There is another variation called GELU, G-E-L-U, Gaussian error linear unit, right? So GELU of x is x times phi of x. What is this phi of x? Phi of x is the cumulative standard normal distribution. What is that? So it is x times p of, is a standard cumulative function. This is basically captures the quartile, the percentile rather than the signal. Okay, so this is GELU. Now let us look at another paradigm of activation, which is called GLU, right? This is gated linear unit. We'll talk about gating mechanism in the LSTM GRU part. Okay, now what is this GLU activation? So let us assume that you have there's hidden neurons, right? Inputs and hidden neurons. Okay, and let's say A1, A2, A3, A4, they are pre-activation values, right? In GLU, what you do, you just duplicate this one here. Okay, duplicate this. So let's say A1, A2, A3, A4. Okay, you pass it through some weight, W weight. This weight is different from this weight, by the way. Okay, and then what you do, and then you also have a bias, right? So this will be A so W transpose A plus B, okay, and you pass it through a sigmoid. So you have original A and you have a sigmoid of A, sigmoid of A or B, whatever, sigmoid of A comma B, right? And then you do gating. And what is this gating? This gating is an element wise multiplication. Remember, A is a vector which consists of A1, A2, A3, A4. The sigmoid is also a vector, right? So let's say this is A1 is 0.4, this is 0.5, this is 0.6, 0.1, right? And after sigmoid, let's say this value is going to be 0.9, let's say this is 0, right? Whatever 0.01, this is these are all imaginary numbers, by the way, okay, these are all imaginary numbers. So 0.2 or something like that, 0.8, okay. So when we do element wise multiplication, this will basically be 0.4 times 0.9, 0.5 times 0.01, 0.6 times 0.2, 0.1 times 0.8, and this will produce another set of A, A1, A2, A3, A4. Now these weights are learnable, these are trainable parameters. B is also a trainable parameter. All right. Here this is called gating mechanism because you will essentially train or learn these W's in such a way that some of these outputs, but these outputs will control the impact of this pre-activation values to the next layer. Let's say this is 0.9, that means you give more weightage here. This is 0.01, you give less weightage here. This is 0.2, you give slightly less weightage here, and so on and so forth. Okay, so you can think of, so these inputs, okay, you think of so this is A1, A2, A3, A4, you think of a GLU layer here, GLU, okay, which will produce numbers. GLU, remember, is a parameter W and P that you need to learn. Okay. So the next part, the next activation function is called Swiss activation. There are tons of activation functions which are publicly available, and people are still proposing new activation functions every day. Swiss activation is very interesting. This is so Swiss X is X times sigmoid beta X. Beta is again a trainable parameter, right? So essentially you are multiplying a non-linear part with a linear part, right? So the beauty of this Swiss function is as follows. So if let's say beta is 10, it will look like this. If beta is my drawing is not good, by the way. Beta is 0.1, it looks like this. If beta is 1, it looks like this. So if you see this, when beta is 10, it is almost a ReLU function. Okay. If beta is 1, it is basically a linear. Okay. And you have things in between. So with the tuning of beta, you can get linear function, ReLU function, and so on and so forth. Sometimes this is also called SILU, SILU, sigmoid linear unit. Okay. And in another paper, people combined Swiss activation and GLU activation, and people call it Sui GLU. Looks like this. X, so G of X is X Swiss WX plus B. Okay, this is this element wise dot product that we used here. All right, there are many other activations like soft plus, right, max out, and so on and so forth. Some of them are computationally challenging, computational complex. Remember this gradient, so we need to take the gradient of the activation, right? Therefore this should be computationally easy, right? So that is another factor. All right, so the next part of the lecture we'll talk about backpropagation. Let's draw a diagram again. Okay, a simple multilayer perceptron, and let's assume that there is only one hidden state and only one output. Okay, let's make our job simple. So this is ith input, jth neuron, kth output, right? So this is W ji1 and this weight W kj2. This is input xi. Now, as I mentioned, every neuron has two operations, right? A and activation H, which will produce this Z, right? So let us bifurcate this up to two activation, right? Two operation. Okay, let's assume that in this component A is being computed, here Z is being computed. All right, yes. Okay, W kj2. Okay, so when we compute this yk, right, we also know, let us assume that you also know the ground truth for this input, right? And the ground truth is tk. So what is the loss? The loss is yk minus tk, and let's say here the loss or the error is a square error, right? Square loss. So error E is sum over total error, right? So how many outputs are there? There are k outputs, yk minus tk square, and we take this half because later on we need to take the derivative. This 2 and half will cancel out. So this is my error. Now we will take the derivative of this error with respect to all the weights, and we'll update all the weights, right? So we'll take the derivative of this error. This is the derivative of the error, right? Let's say with respect to w, some w, okay, and this will be, let's say this is a convex function, so weight will be updated. This is the learning rate, standard concept, standard machine learning concept, stochastic gradient descent, and this will be my updated error, updated weight. Okay, so let's first focus on this weight update, wkj2. So to update this, we need to take the partial derivative of it with respect to wkj2. Okay, that means we need to take the derivative of this with respect to wkj2, right? So this is x square, so 2x, so 2 and this half will cancel out, so this will be sum over yk minus tk, k equals to 1 to k. Okay, now we also need to take the derivative of this with respect to, so the partial derivative of yk minus tk with respect to wkj. Now when you take the derivative of tk, tk is a constant, it's a ground truth, so this will be 0. What is yk? Yk, what is yk? Yk is sum over, okay, so I forgot to mention another thing. Let us assume that the activation here at the output is a linear activation, hs equals to x. Whatever input you get, that's going to the output. So yx is essentially the aggregation, right? W kj, where j goes from 1 to m, there are m number of neurons, and z j. Now when I'm and this is 2, when I'm taking this derivative with respect to kj2, only that element will contribute, right? So this is essentially, this is going to be, and this is 1, okay, this is 1, doesn't matter, there is only one layer, but still it's okay. So the output of this will be this, so the total output like this. Now remember here, so this is straightforward because there is only one hop. Now when we update this one, this is difficult, right? So del E del W ji 1, okay. Now from here, this is error, this is E, till here what are the operations that we have performed? We have performed Z and A, so we have to use the chain rule, right? So this is essentially del E del Z one del Z j1 del W ji1, okay. Now what is this? Let's look at this one first. Now del Z j1 del W ji1 is what? So we have another intermediate part, which is this one, because I am now moving from this to this, right? There is an intermediate part which is A. You have to take the partial derivative with respect to A also. Del A 1 del A j1 del W ji1, okay. What is this? What is this Z? So Z j1 is nothing but this activation function. Let us assume that the activation function here is tan h, okay. So this is essentially tan h of aj1. What is the derivative of this? This is 1 minus tan h square, right? Which is, this is the derivative, right? Which is, this is derivative, this is 1 minus square. So this will be 1 minus zj1 square, this part, this part. Now what is this part? Think about it. So aj here, aj1 is nothing but the weighted sum, right? Weighted sum of all the inputs, right? And when we are taking the derivative with respect to wji1, only the corresponding input will be responsible. All the other inputs will act as constant, right? So this derivative will produce xi. If it is not clear, please go back and check the chain rule. Okay, so this is my result for this component. What about the other component? Del E, del zj1, right? This is zj1 and del E. So E is what? E is this one, right? Where we already know that y is this one, right? So when we take the derivative of this with respect to z is this one. When you take the derivative of this with respect to zg, what will happen is that first this will act as simple x squared 2x, right? 2 and 2 will cancel out when there is a derivative of this, and then we need to take the derivative of that component again. Only what will happen? Only the corresponding z will basically come out, right? We are taking the derivative of this with respect to z, so only w part will come out. Okay, so del E, let me write here, del E del zj1 is sum over yk minus tk, k is to 1 to k. Okay, and then the partial derivative of this yk minus tk j1. Okay, and this is yk minus tk. Okay, the tk is constant here, so yk is this one, so this will result in w kj2. The final derivative del E del wji1 will consist of this, okay, which is sum over k goes to 1 to k yk minus tk wkj2, right? So this part and this part, which is 1 minus zj square xi. Now think about it. So this is this delta E, right, with respect to wji1. So when you do the forward pass, this is back propagation, backward pass, right? When you did the forward pass, you already stored the value of y, the output. You also know the ground truth t, and what is this wkj? Wkj2 is the existing weight, right, which will be updated, right? So existing weight is also known to you. Zj is also known to you. This was stored during the forward pass, and xi is the input. So all the components are known to you. Therefore, this gradient will also be known to you, and we will use this learning rate, multiply this with the gradient, and that is going to give you the updated wji with respect to wji at ith layer. Now think about it. As we increase the number of layers, okay, you will have to multiply several such gradients, right? Think about it. So this error, and there are, let's say, hundreds of layers, right? And you want to update the weight of the first layer, so you have to take the gradient of the error with respect to that weight, right? So all the intermediate components will be considered while taking the derivative, right? And let's assume that the gradients of the gradient of the error with respect to these components are very, very small, right? So what will happen? The result is a lot of zeros, lot of small numbers will be multiplied, and therefore the resultant multiplication value, the multiplication output, is going to be very small. So this is called vanishing gradient in case of multi-layer perceptron feed forward network. So as we increase the number of layers, the contribution of the first layer, the contribution of the error in updating the values of the weights at the initial layers will be very small. So initial layers weight will not be updated at all, right? This is vanishing gradient. We'll discuss vanishing gradient in RNN, recurrent neural network, right? There are many ways to address the vanishing gradient problem, by the way. So that's it. This is backprop. What are the parameters here? The parameters are all the weights, bias, right? Learning rates. Learning rate is a hyperparameter. Sometimes we fix learning rate, and sometimes we also use some sort of dynamic learning rate, with respect to epoch. So sometimes we use something like this: 1 minus decay times epoch time decay learning rate. Also for regularization, right? Because what happens is that neural networks, if you have small amount of data, deep neural network, the models will overfit. There are many ways to address this. One is early stop. You don't need, you will not allow the model to basically produce 100% accuracy or zero error in your training set, on your training set, right? So you stop the model early before convergence, right? The other option is, of course, L1, L2 regularizer, right? So what you do, that along with the error, right, whatever error you have, let's say square error or log likelihood, some sort of cross entropy error, you also add a regularizer there, right? The other option is called dropout, where you essentially freeze a fraction of neurons for being updated. So you are basically making the neural network sparse, right? Again, there are different ways to update this thing, identify the neurons which need to be dropped out. Okay. There are many concepts, important concepts there in deep learning which we have not covered, because this is not a deep learning course. There are, as I mentioned, there are many deep learning courses available even on NPTEL. You can check them out. Vanishing gradient problems I mentioned, exploding gradient problems are also mentioned. Some of these things are written in the book also, my book. So you can look at chapter 2 for detailed description of some of the concepts that are discussed here. Okay, with this I stop here, and this was about the introduction of neural network and deep learning, right? In the next lecture we'll move to the main concept of large language models. Thank you.